A spacecraft built with 1970s technology is currently traveling through interstellar space more than 24 billion kilometers from Earth. Voyager 1 weighs less than a compact car, generates less power than a household microwave, and has been operating continuously since its launch in 1977. In 2012, it became the first human-made object to cross the heliopause and enter the local interstellar medium, the sparse plasma that exists between the stars. Even now, it continues to transmit data across a distance so great that its radio signals require more than 23 hours to reach Earth at the speed of light. Within the next decade, those signals will cease as the spacecraft's power supply finally declines below operational levels. But the end of communication is not the end of the journey. Voyager 1 will continue moving through the galaxy at approximately 17 kilometers per second for tens of thousands, millions, and eventually billions of years. Following its future trajectory provides a rare opportunity to understand astronomical distance not as an abstraction, but as a measurable physical reality. What Voyager 1 actually is and what it carries into the dark. Voyager 1 is a spacecraft that measures 3.7 meters across its high-gain antenna dish, with a central bus roughly the size and shape of a large household appliance. It weighs approximately 721 kilograms. Its onboard computers execute thousands of instructions per second, a figure that any modern smartphone exceeds by a factor of roughly 1 million. It was designed, engineered, assembled, and launched in a period when personal computers did not exist, when the human genome had not been mapped, when no exoplanet had ever been confirmed around another star, and when the extent of the heliosphere was a theoretical prediction rather than a measured boundary. The people who built it are mostly retired or dead. The original mission documentation has been preserved on formats that require special hardware to read. The spacecraft itself, however, has never stopped. Voyager 1 launched on September 5, 1977 on a Titan IIIe Centaur rocket from Cape Canaveral, Florida. Despite launching second after its twin Voyager 2, which departed on August 20th, it was placed on a faster trajectory and reached Jupiter first, in March 1979. It flew past Jupiter, using that planet's enormous gravitational field to slingshot itself onto a trajectory towards Saturn, which it reached in November 1980. The Saturn encounter included a close pass by the moon Titan, chosen deliberately because of its thick atmosphere and its scientific interest to the mission's planners. That close pass by Titan deflected Voyager 1's trajectory northward out of the ecliptic plane, the flat disk in which the planets orbit the Sun, permanently ending any possibility of further planetary encounters. The grand tour was over. The interstellar mission, never the original intention, had begun. For the next 3 decades, Voyager 1 crossed the outer heliosphere, the vast region of space still within the Sun's sphere of influence. It measured the solar wind, the constant flow of charged particles streaming outward from the Sun in all directions, growing progressively weaker with distance. It passed through the termination shock in 2004, the boundary where the solar wind abruptly slows from supersonic to subsonic speeds as it presses against the resistance of the interstellar medium beyond. It crossed the heliosheath, the turbulent transition region between the termination shock and the outer boundary of the solar system's influence. And in August 2012, it crossed the heliopause, the outermost boundary where the Sun's particle wind gives way entirely to the interstellar medium, the space between star systems. Voyager 1 became the first human-made object to enter true interstellar space, and the scientific instruments it carried sent back measurements that revised the models scientists had built to describe that environment. What Voyager 1 carries with it beyond its scientific instruments is a golden record, a 12-inch gold-plated copper disc enclosed in an aluminum cover and attached to the spacecraft's exterior. The record was designed by a committee including Carl Sagan, Anne Druyan, Frank Drake, Timothy Ferris and others, and it contains 115 images encoded in analog format, greetings in 55 human languages, sounds of Earth including rain, wind, ocean waves, bird calls, and a human heartbeat, and 90 minutes of music spanning diverse human traditions, from Bach to Chuck Berry to traditional music from cultures across the world. The cover carries instructions for playing the record and diagrams indicating the location of Earth relative to 14 known pulsars, using the pulsar's rotation frequencies as a coordinate system that any civilization with sufficient science could decode. The uranium-238 electroplated onto the cover serves as a clock. Its radioactive decay half-life of 4.5 billion years means that a finder who could measure the remaining uranium would know when the record was made. Carl Sagan understood, when he championed the golden record, that the probability of it ever being found and played was extraordinarily small. He understood that interstellar space is so vast and so empty that the chance of any object crossing near the probe within any relevant time frame was negligible. The record was not primarily a message to extraterrestrials. It was a statement about the civilization that sent it, a decision to include something human in the first object humanity ever sent beyond the solar system, because that felt like the right thing to do. The record will travel with Voyager 1 through the dark for billions of years, intact, unread, and permanent in a way that nothing on Earth, no building, no monument, no digital archive can be. It is the most durable human artifact ever created, and it will outlast everything else we have made. What Voyager 1 does not carry is fuel for deceleration or course changes. Its attitude control thrusters use small amounts of hydrazine, and those reserves are finite, already nearly exhausted. When the hydrazine runs out, Voyager 1 will lose the ability to maintain the orientation of its antenna toward Earth, and the communication link will end. After that, Voyager 1 will be a free drifting object, subject only to gravity, and moving at whatever velocity it had at the moment of fuel exhaustion. That velocity, approximately 17 kilometers per second relative to the Sun, is not going to change in any meaningful way for billions of years. In the near vacuum of interstellar space, there is essentially nothing to slow it down. Newton's first law applies in its purest possible form. An object in motion stays in motion at constant velocity unless acted upon by an external force. The external forces available in interstellar space, gravity from distant stars, the tiny drag of the sparse interstellar medium, are so small that they will alter Voyager 1's velocity by less than a meter per second over the next 100,000 years. The probe is going where it is going, at the speed it is going, and nothing will change that. The velocity that sounds fast and the distance that makes it crawl. Voyager 1 currently moves at approximately 17 kilometers per second relative to the Sun, or roughly 61,000 kilometers per hour. These numbers deserve to be held alongside some reference points before they are placed against interstellar distances, because otherwise the human brain processes them as fast, files them under impressive, and moves on without registering the crushing inadequacy that these numbers represent at the scale of what lies ahead. A commercial airliner travels at approximately 0.25 kilometers per second. Voyager 1 moves roughly 68 times faster than a commercial airliner every second, continuously, without stopping. A high-powered rifle bullet travels at approximately 1 kilometer per second. Voyager 1 moves about 17 times faster than a rifle bullet, continuously, for decades. The Parker Solar Probe, the fastest spacecraft humanity has built, achieved approximately 163 kilometers per second at its 2024 closest solar approach, making it roughly 10 times faster than Voyager 1. But the Parker Solar Probe's extreme velocity is achieved through gravitational acceleration during a close solar pass and is not maintained as a cruise speed. Voyager 1's 17 kilometers per second is its actual sustained velocity through interstellar space. It is the fastest any object from Earth has ever maintained for an extended period in deep space. Against everyday experience, 17 kilometers per second is extraordinary. Against interstellar distances, it is essentially nothing. The light year, the distance light travels in 1 year, is approximately 9.46 trillion kilometers. Voyager 1 covers approximately 536 million kilometers per year, which is 0.0000567 light years. To travel 1 complete light year at Voyager 1 speed requires approximately 17,650 years. The nearest star to our Sun, Proxima Centauri, is 4.24 light years away. At 17 kilometers per second, Voyager 1 would need approximately 74,800 years to reach Proxima Centauri's distance, roughly 18 times the entirety of recorded human history. And Voyager 1 is not pointed at Proxima Centauri. It is travelling in a different direction entirely. The gap between the fastest sustained speed humanity has achieved in space and the speeds needed to make interstellar travel meaningful is not a gap of degree. It is a gap of kind. At 17 kilometers per second, travelling 1 light year takes roughly 17,650 years. The Milky Way galaxy is approximately 100,000 light years in diameter. Crossing the galaxy at Voyager 1 speed would take approximately 1.76 billion years. The Sun is approximately 26,000 light years from the galactic centre. Reaching the galactic centre from the Sun, not from Earth, but from the Sun's current position in the galaxy, at Voyager 1 speed would take approximately 459 million years. These numbers do not respond to engineering ambition. They are set by physics and geometry. The specific trajectory Voyager 1 is on carries it toward the constellation Ophiuchus in the rough direction of the current position of the star AC plus 79, 3888 in the constellation Camelopardalis, sometimes designated Gliese 445. This star is currently approximately 17.6 light-years from Earth and is itself moving through the galaxy at a velocity that will bring it somewhat closer to the solar system over the next tens of thousands of years. The encounter, such as it is, will occur in approximately 40,000 years and will involve Voyager 1 passing within approximately 1.6 light-years of that star's position. To be very clear about what this means, 1.6 light-years is approximately 15 trillion kilometres. The closest, the most distant human-made object will come to any star system in the next 40,000 years is still 15 trillion kilometres, a distance so vast it makes the gap between Earth and Voyager's current position look small by comparison. There will be no dramatic encounter, no gravitational capture, no close pass of any planetary system. Voyager 1 will not come within detectable distance of any planet orbiting any star for the entire geological future of Earth as a habitable world. Understanding this velocity in relation to these distances requires something more than arithmetic. It requires sitting with the specific contrast between what 17 kilometers per second means in the context of everyday experience, a number that the brain cannot help but process as fast, and what it means against the canvas of interstellar space, where it is so slow as to be negligible relative to the distances involved. Every discussion of interstellar travel, every proposal for reaching other stars, every calculation of mission duration must start from this baseline. The fastest sustained velocity achieved by any human-made object is so small relative to interstellar distances that even a factor of 10 improvement would leave the mission impractical, and a factor of 100 improvement would still require centuries to reach the nearest star. Voyager 1's velocity defines the floor of the problem. The ceiling of what is needed is thousands of times higher. In 1,000 years, still closer to home than you think. In the year 3025, 1,000 years from now, Voyager 1 will have been travelling through interstellar space for approximately 1,013 years since its 2012 heliopause crossing. At 17 kilometers per second, it will have covered approximately 537 billion additional kilometers since the present day. Adding this to its current distance of roughly 24 billion kilometres gives a distance of approximately 561 billion kilometres from the Sun. This number has 12 digits and occupies a position on the astronomical distance scale that, without context, means very little. The context is what matters. The orbit of Pluto, at its most distant point from the Sun, reaches approximately 7.4 billion kilometres. In 1,000 years, Voyager 1 will be approximately 75 times farther from the Sun than Pluto's most distant orbital position. The heliosphere, the bubble of solar influence that Voyager 1 crossed in 2012, extends to roughly 18 billion kilometres at the heliopause. In 1,000 years, Voyager 1 will be roughly 30 times farther from the Sun than the outer boundary of the solar system's direct influence. It will be deep in the interstellar medium by any measure, surrounded by the thin plasma and magnetic fields of the region between star systems rather than any remnant of solar influence. But the nearest star, Proxima Centauri, is approximately 40.2 trillion kilometres away. In 1,000 years, Voyager 1 will have covered approximately 537 billion kilometres, which is roughly 1.3% of the distance to Proxima Centauri. After 1,000 years of continuous travel at a speed that exceeds any projectile or aircraft human beings have created, Voyager 1 will be about 1/75th of the way to the nearest star. It is worth pausing on this specific number. 1,000 years ago, the Norman conquest of England had just occurred. The Song dynasty was governing China. Leif Erikson had recently become the first European to reach North America. The Aztec Empire did not yet exist. The Magna Carta was 2 centuries in the future. The entire sweep of European history, from the High Middle Ages through the Renaissance, the Scientific Revolution, the Industrial Revolution, the 20th century's wars and its technological explosion. All of it would fit inside the time Voyager 1 will have been travelling, and in that entire span of time, it will have covered 1/75th of the distance to the nearest star. The interstellar environment Voyager 1 crosses during this first millennium is the local interstellar medium, specifically the region within the local bubble, a cavity in the interstellar medium approximately 300 light-years across that was evacuated by supernova explosions roughly 10 million years ago. The local bubble has a relatively low density of interstellar matter, meaning Voyager 1 encounters fewer particles per cubic centimetre than it would in denser regions of the galaxy. Within the local bubble, Voyager 1 is currently passing through the local interstellar cloud, a warm, partially ionized region of somewhat higher particle density that extends a few light-years in various directions. The physical properties of this environment, its temperature, density, magnetic field strength and direction, are precisely what Voyager's plasma wave science instrument and magnetometer have been measuring since the heliopause crossing. These measurements are scientifically irreplaceable and will remain the only direct samples of the local interstellar medium from a human-made instrument for potentially decades after the mission ends. The stellar neighbourhood visible from Voyager 1's position in 1,000 years will be essentially indistinguishable from what it is now. The stars are so far away, and their proper motions, their velocities across the sky as seen from any given vantage point, are so slow that no visible change in the star field would be apparent to the naked eye over 1,000 years. The Sun, from Voyager's position in 1,000 years, will appear as a point of light roughly 1/10,000th as bright as it appears from Earth. The entire solar system, the planets, the asteroid belt, the Kuiper belt, will all be invisible. The Sun will be a star like other stars, distinguished only by its known distance. Voyager 1 will carry no information about whether anything has changed on Earth in the 1,000 years since the present, because the last signal from the spacecraft will long since have faded. It will be moving through the dark without awareness, without guidance, and without any connection to the civilization that created it. In 10,000 years, the last ice age as a reference point. 10,000 years places Voyager 1 at approximately 5.37 trillion kilometers from the Sun, roughly 0.568 light-years. This is a distance that, for the first time, can be meaningfully expressed in units of light-years, rather than the unwieldy billions or trillions of kilometers that describe shorter distances. At 0.568 light-years, Voyager 1 will be more than halfway through the thickness of the Oort cloud's inner region, the vast spherical shell of icy bodies that orbits the Sun at distances from roughly 0.5 to as much as 2 or 3 light-years. Whether Voyager 1 will physically interact with any Oort cloud object over the next 10,000 years, whether it will collide with a cometary nucleus or experience a measurable gravitational deflection from a nearby body, depends on the actual density and distribution of Oort cloud objects in the specific corridor it crosses, which are not precisely known. The best estimates suggest a collision probability that is negligibly small, far less than 1% over this time frame. 10,000 years is the approximate duration of what geologists and historians call the Holocene epoch, the current interglacial period that began when the last glacial maximum ended, and the ice sheets covering much of the northern hemisphere began their retreat. 10,000 years ago, the Laurentide ice sheet still covered significant portions of North America. Sea levels were lower by roughly 60 meters because so much water was locked in ice. The Sahara Desert was a savanna with lakes and rivers. Agriculture had only recently begun to develop independently in a handful of locations around the world. The total human population was perhaps 5 to 10 million people. In the 10,000 years since that moment, humanity invented writing, mathematics, astronomy, philosophy, engineering, medicine, the printing press, steam power, the internal combustion engine, nuclear physics, quantum mechanics, the internet, and space travel. It built and destroyed hundreds of civilizations, developed dozens of major languages, produced an incomprehensible quantity of art, literature, music, and architecture, fought wars that killed hundreds of millions, and developed technology capable of altering the climate of an entire planet. All of that happened in the time that Voyager 1 will travel to reach 0.568 light-years from the Sun. At that point, the probe will still have 3.67 light-years to go before it reaches the current distance of Proxima Centauri. And Proxima Centauri is the nearest star. From Voyager 1's position at 10,000 years, the Sun will appear as a bright star, roughly magnitude -3, comparable in apparent brightness to how we see Jupiter from Earth, clearly visible in any direction with the naked eye, but reduced to a single point of light, indistinguishable in its basic appearance from any other bright star. No planet in the solar system will be visible. No sign of Earth's existence will be detectable from this distance, using any technology comparable to current human capability. The star patterns around Voyager 1 will begin to show very slight changes from their present configuration, because over 10,000 years, the proper motions of nearby stars become detectable. The constellation patterns familiar from Earth will still be broadly recognizable, but with small distortions, primarily from the motion of the nearest and fastest moving stars. The Oort cloud that Voyager 1 is crossing at this distance is the least understood region of the solar system. It has never been directly observed. Its existence is inferred from the dynamical properties of long-period comets, whose nearly parabolic orbits trace back to a reservoir at these distances. The total number of objects in the Oort cloud is estimated at 1 to several trillion, ranging from small icy fragments to objects hundreds of kilometers across. Despite this large number, the volume of space they occupy is so enormous that the average spacing between objects is vast. If Voyager 1 were to travel through the densest parts of the Oort cloud for 10,000 years without any deflection, the probability of a direct collision with any object is calculated to be extremely low. The Oort cloud is not a crowded place by any measure humans would recognize. It is a sparse scattering of icy bodies spread across the most enormous volume of space in the solar system, and Voyager 1 will cross through it in complete silence, unable to detect a single one of them, its instruments long since silent. In 40,000 years, the closest any star will come. In approximately 40,000 years, an event will occur that is in some ways the most dramatic point in the entire foreseeable future trajectory of Voyager 1, and in other ways illustrates precisely the scale problem that makes all discussions of interstellar travel so disorienting. Voyager 1 will make its closest approach to any star system for the entire future that can be reliably calculated. That star system is the current AC plus 79 3888 in the constellation Camelopardalis, a reddish dwarf star now known to be approximately 17.6 light-years from Earth. This star is itself moving through the galaxy in a direction that will bring it somewhat closer to the solar system over time. The combined effect of Voyager 1 moving away from the Sun in the star's general direction and the star moving somewhat toward the solar system produces a closest approach of approximately 1.6 light-years in roughly 40,000 years. 1.6 light-years is approximately 15 trillion kilometers. It is roughly 38 times the current distance between the Sun and Voyager 1. It is roughly the distance light travels in 1 year and 7 months. This is the closest any human-made object will come to any star system for the next 40,000 years, and it will still be an utterly remote encounter, with no prospect of gravitational capture, no possibility of any planetary encounter, and no physical interaction of any kind between the spacecraft and the star system it nominally approaches. Voyager 1 will pass by this system at 1.6 light-years, moving at 17 kilometers per second relative to the Sun, and will continue into the void beyond, having made its closest approach to another stellar system without coming within 10 trillion kilometers of anything interesting. But place 40,000 years in human terms, and the number becomes staggering for a different reason. 40,000 years ago is roughly the date of some of the oldest known cave art, the ochre handprints and animal figures preserved in sites like Chauvet Cave in France and Sulawesi in Indonesia. It is the period of the Upper Paleolithic, when anatomically modern humans in Europe were living in small mobile groups, hunting mammoths and aurochs, painting extraordinary images on rock walls by firelight, and wearing jewelry carved from animal bones. The concept of agriculture was 30,000 years in the future. The concept of writing was 35,000 years in the future. The concept of a civilization was roughly 38,000 years in the future. And Voyager 1, launched by the civilization that eventually developed from those cave painting ancestors, will in that same span of time have crossed 40% of the distance to the nearest star, only to still be over 2 light-years short of its destination. The star that Voyager 1 approaches in 40,000 years is not a particularly notable object. It is a Type M red dwarf, dim and cool, with a luminosity a small fraction of the Sun's. Whether it hosts any planets is unknown. Whether those planets, if they exist, have any interesting properties is unknown. It is not the kind of star that a civilization would choose as a target for exploration. The only reason it is astronomically significant for Voyager 1's trajectory is that the geometry of Voyager's current path and this star's proper motion happen to produce a closer approach than any other star in the calculable future. The universe is indifferent to whether the closest encounter is with an interesting star or a dim red dwarf. The trajectory determines the destination. After the 40,000-year flyby of this system, Voyager 1 continues into the deeper Milky Way. Its next significant stellar encounter will be a pass within approximately 0.3 light-years of the star. TYC 313552-1 in approximately 230,000 years, and this will be the closest approach any spacecraft currently travelling through interstellar space will make to any star in the foreseeable, calculable future. Even that approach, at 0.3 light-years, is still nearly 3 trillion kilometres. Still an utterly remote non-encounter that would involve no physical interaction between the probe and the star system. In neither case will Voyager 1 have done anything that a sensible person would describe as visiting another star. It will have passed nearby in the same way that two ships on opposite sides of a city might be said to have passed near each other while navigating their respective courses. The Oort cloud Voyager 1 will never know it is crossing. The Oort cloud is the outermost structure of the solar system, a vast spherical shell of icy objects that extends from approximately 2,000 to 100,000 or more astronomical units from the Sun, depending on which definition and which theoretical model is used. It is in some respects the most important structure in the solar system for understanding the delivery of comets to the inner solar system and the bombardment history of the planets, and in other respects the most mysterious, because it has never been directly observed. No telescope has ever imaged an Oort cloud object in its native location. No spacecraft has ever passed through it while carrying functioning instruments. Its existence is inferred from the dynamical properties of long-period comets, those with orbital periods greater than 200 years, whose Keplerian orbits trace back to a source at these enormous distances. The Oort cloud is simultaneously one of the most scientifically important structures in the solar system and one of the least understood. Voyager 1 is currently in the inner fringe of the Oort cloud region by some definitions, though the heliopause it crossed in 2012 is interior to even the inner Oort cloud boundary in most models. By the time Voyager 1 reaches 1,000 years from now, it will be well within the inner Oort cloud's estimated extent. It will spend roughly another 27,000 years crossing through the Oort cloud before emerging on the far side at distances above 100,000 astronomical units. During this entire 30,000-year transit through the solar system's most remote region, Voyager 1 will be completely incapable of detecting, measuring, or characterizing any of the objects around it. Its instruments will have gone dark years to decades after the present. Its transmitter will have fallen silent. Its attitude control will have failed when the hydrazine ran out. The probe will be a tumbling, silent, frozen object drifting through the cloud without any ability to report what it encounters. This is one of the deeper ironies of the Voyager mission. The probe that gave humanity its first direct measurements of the interstellar medium beyond the heliopause will pass through the Oort cloud, the region most planetary scientists would most urgently want sampled by any instrument, and will do so blind and silent. A future mission to the Oort cloud with functioning instruments would represent a revolutionary scientific advance. Such a mission has never been funded, and the propulsion challenges involved in reaching Oort cloud distances in a scientifically useful time frame, say a few decades rather than centuries, require velocities significantly higher than Voyager 1's current speed. An Oort cloud mission at 5 times Voyager 1's speed would still require 15,000 years to reach the outer Oort cloud boundary. At 50 times Voyager 1's speed, the outer boundary is reached in 1,500 years. Still well beyond any mission planning horizon, the comets of the Oort cloud formed in the inner solar system at roughly the same time as the planets, from the same disk of gas and dust that surrounded the young Sun. They were subsequently scattered to their current locations by gravitational interactions, primarily with Jupiter and Saturn, during the early period of planetary migration, when the outer planets were in less stable orbits than their current ones. The Oort cloud comets therefore preserve material from the same region of the early solar nebula that produced Earth, Mars, and the inner solar system bodies, but frozen in a cold, dark environment for 4.5 billion years, with minimal processing since their ejection. Their composition encodes information about the chemistry of the early solar system in a form that is largely inaccessible from Earth-based observation. Voyager 1 will pass through this archive of primordial material without leaving any scientific record of having been there. The probe that extended humanity's observational reach to the heliopause and beyond will drift through the solar system's most remote and scientifically valuable unvisited region as nothing more than a piece of tumbling metal and plastic, carrying a golden record that no Oort cloud comet can read, moving at a speed too slow to be interesting and too fast to linger. The Oort cloud will not notice its passage. Voyager 1 will not notice the Oort cloud, and in 30,000 years, the probe will emerge on the far side of the solar system's outermost structure into the deep interstellar medium, as silent as it went in, as dark as it has been for decades, and as unchanged as a piece of metal in a vacuum can be. In 100,000 years, a sky that no longer recognizes itself. 100,000 years from now, Voyager 1 will be approximately 53.7 trillion kilometers, or approximately 5.68 light-years from the Sun. This places it comfortably beyond the current distance of Proxima Centauri, which is 4.24 light-years away. In 100,000 years, Voyager 1 will have covered more than the distance to the nearest star, measured from its launch point. But it will have done so in a direction entirely different from that of Proxima Centauri, and will have moved to a position in the galaxy that puts it deep in the interstellar medium without having meaningfully approached any star system. 100,000 years is a number that begins to blur the distinction between human history and geological time. At 100,000 years ago, the last common ancestor of all living humans was walking somewhere in Africa. Homo sapiens had not yet spread significantly beyond the African continent. The major dispersal events that would eventually populate every habitable region of Earth had not occurred. The species Homo neanderthalensis still existed in Europe and Western Asia. Ice sheets covered much of the high latitudes. The megafauna of Europe, Asia, and the Americas, mammoths, woolly rhinoceroses, giant ground sloths, cave lions, were still present in large numbers. 100,000 years of evolution, migration, adaptation, and eventually civilization have produced the species that built Voyager 1. In another 100,000 years, human biological evolution may produce changes as significant as those that occurred in the previous 100,000, though the increasing role of culture and technology in human development complicates any simple extrapolation. The night sky, as seen from Earth in 100,000 years, will be noticeably different from the sky we see tonight. Every star in the sky has a proper motion, a velocity component perpendicular to the line of sight that moves it gradually across the background of more distant objects. For nearby stars, this motion is measurable on timescales of decades. Over 100,000 years, it accumulates to produce changes in constellation patterns that would be striking even to a casual, naked eye observer. The constellation Orion, one of the most recognizable patterns in the Northern Hemisphere winter sky, will have distorted significantly because its component stars are at different distances and have different proper motions. Betelgeuse, the red supergiant marking Orion's right shoulder, will have moved noticeably relative to the other stars. Sirius, the brightest star in Earth's night sky, will have shifted significantly in position, because it is a relatively nearby star moving at a high proper velocity. The overall stellar landscape of Earth's sky in 100,000 years will be recognizable in its general character, but different in its specific patterns in ways that would require a detailed star atlas to navigate. From Voyager 1's position at 5.68 light-years, the Sun will still be a bright star, visible without magnification, but reduced to a stellar point. The exact appearance of the sky from Voyager 1's perspective in 100,000 years depends on the detailed proper motions of all the nearby stars. But the general principle is that Voyager 1 will be surrounded by stellar distances of several light-years in all directions, with no star particularly dominant, and the galaxy structure beginning to be apparent as a band of light from the combined glow of the Milky Way's disk. The galaxy itself, which appears from Earth as a band of light crossing the sky on clear dark nights, will look structurally similar from Voyager 1's position in 100,000 years to how it appears from Earth today, because Voyager 1 has moved only a tiny fraction of the galaxy's diameter. The galactic disk is approximately 100,000 light-years across. In 100,000 years, Voyager 1 will have moved approximately 5.68 light-years, which is 0.00568% of the galactic diameter. The galaxy will look essentially the same. The scale of the galaxy mocks the scale of Voyager 1's achievement, and this is the lesson that tracing the probe's trajectory into deep time most powerfully teaches. The distance to the nearest star is not a significant fraction of anything. It is the first step in a walk across an incomprehensibly vast landscape that our fastest spacecraft has spent 100,000 years beginning and has not meaningfully started. The silence that falls before any of this happens. All of the scenarios described in the preceding chapters, the 1,000-year position, the 10,000-year position, the 40,000-year closest stellar approach, the 100,000-year position beyond Proxima Centauri's current distance, will occur without any signal from Voyager 1 reaching Earth. The silence that will precede these milestones is not a distant event, it is imminent. The specific mechanics of when and how Voyager 1's signal will be lost for the last time deserve careful attention, because the transition from an active mission to a silent drifting object is the transition that makes all subsequent history of the spacecraft purely a matter of physics rather than science. Voyager 1's power comes from 3 radioisotope thermoelectric generators, RTGs, that convert the heat produced by the radioactive decay of plutonium-238 into electricity via thermoelectric junctions. Plutonium-238 decays at a rate characterized by its half-life of approximately 87.7 years, meaning that every 87.7 years, the heat output, and therefore the electrical output, falls by half. At launch in 1977, the RTGs produced approximately 470 watts of electrical power. By 2024, that output had declined to approximately 220 to 230 watts. The decline is continuous and relentless at approximately 4 watts per year, and it cannot be stopped or reversed. As the power output falls, the mission team at NASA's Jet Propulsion Laboratory has systematically turned off instruments and heaters to keep the remaining systems operational, prioritizing the transmitter and attitude control as the most essential systems for maintaining the mission. The transmitter that sends Voyager's signal home operates at approximately 23 watts of radio frequency power. As RTG output falls, keeping the transmitter operational while also running the computers and attitude control system becomes progressively harder. The mission team has estimated that at least one science instrument could remain operational until approximately 2025 to 2026, with engineering telemetry possibly continuing for a few years beyond that. The transmitter itself will eventually fall below the power level needed to maintain a signal detectable by the Deep Space Network's largest antennas, even with the most aggressive noise reduction and signal integration techniques available. The best current estimate is that Voyager 1's signal will be permanently lost to detection capability sometime in the mid to late 2030s. By 2040, the mission will almost certainly be over in any operationally meaningful sense. After signal loss, the physical sequence of Voyager 1's decline continues according to the laws of thermodynamics. The RTGs will continue to produce heat for thousands of years at diminishing levels, because the plutonium-238 has a half-life of 87.7 years and will not be fully decayed to lead 206 until billions of years have passed. But the electrical output will long since have fallen below any useful threshold. The attitude control thrusters will exhaust their hydrazine within the next few years, or have already done so, ending the spacecraft's ability to maintain its antenna orientation. The hydrazine in the thruster lines will freeze solid as the heaters that kept it liquid are turned off to conserve power. The lubricants in any mechanical components will congeal in the cold of space. The spacecraft will slowly adopt a tumbling orientation as there is no longer any torque applied to maintain its pointing. The golden record will be entirely unaffected by any of this. It is a passive physical object, not dependent on power, not mechanical, not subject to any failure mode in the space environment it will occupy. It will remain attached to the spacecraft in its aluminum cover, electroplated with uranium-238, its grooves preserving the sounds of Earth indefinitely. Long after every electronic component on Voyager 1 has been reduced to a useless matrix of radiation-damaged semiconductor material, long after the thermoelectric junctions have degraded beyond any useful function, long after the hydrazine has frozen and the thrusters are dead, the golden record will be exactly as it was on the day it left Earth. It will be the most intact and most durable component of the spacecraft, and the one with the longest theoretical future ahead of it. What Voyager's journey reveals about the shape of space and time. The specific numbers associated with Voyager 1's past and future trajectory are not merely astronomical curiosities. They constitute one of the most vivid demonstrations available of the actual structure of the universe humans inhabit, a structure that is genuinely difficult to hold in mind, and that the trajectory of a specific, real human-made object makes concrete in a way that abstract statistics cannot. Tracing Voyager 1 through time does something to the mind that simply reading about the size of the universe does not. It anchors the scale to a known object, a specific machine built in a specific decade by specific people, and shows what that scale means for that object's future. The first thing Voyager 1's trajectory reveals is that the solar system, enormous as it appears to inhabitants of Earth, is a negligible fraction of even the immediately local cosmic environment. The heliopause, the boundary of the solar system's direct influence, is approximately 18 billion kilometers from the Sun. Proxima Centauri, the nearest star, is approximately 40.2 trillion kilometers away. The ratio of these two distances, the solar system's radius to the distance to the nearest star, is approximately 2,200 to 1. The solar system is not a significant fraction of the distance to the nearest star. It is not a starting point from which interstellar distances seem manageable. It is a region so small relative to the interstellar distances around it that crossing it represents essentially zero progress toward any interstellar destination. The second thing Voyager 1's trajectory reveals is that the timescales required to cross interstellar distances are not compatible with any human institution that has ever existed. 1,000 years is longer than most religions have maintained doctrinal continuity. 10,000 years exceeds the entire duration of documented human civilization. 100,000 years exceeds the total lifespan of Homo sapiens as a distinct biological species by a significant margin. These are the timescales involved in Voyager 1, covering the distance to the nearest star, and they are timescales over which no plan, no mission, no organizational commitment, no cultural memory has ever survived. The spacecraft that will cross this distance does not yet exist. The civilization that will build it has not yet developed the technology, the energy resources, or perhaps the institutional structures needed to undertake such a mission. Voyager 1 makes this not an abstract concern, but a physical reality. This is the distance. These are the timescales. And here is what the fastest thing we have ever sustained in space looks like against them. The third thing Voyager 1's trajectory reveals is about permanence and impermanence at different scales of time. On the scale of a human life, or even a human civilization, Voyager 1 is extraordinarily durable. No building currently standing will be standing in 10,000 years. No language currently spoken will be spoken in its current form in 10,000 years. No political entity, no religious institution, no cultural tradition currently alive will exist in recognizable form in 10,000 years. But Voyager 1, tumbling silently through the interstellar medium, will be essentially unchanged. The metal will not have corroded. The plastic components will have undergone some radiation damage but will retain their physical form. The golden record will be intact. The spacecraft will look very much as it did when it was launched, except for its tumbling orientation and the fading of its paint. This asymmetry between the permanence of Voyager 1 and the impermanence of everything else humanity has made is one of the most thought-provoking features of the mission's future. We have built something that will outlast us, that will outlast our civilization, that will outlast our language, that will outlast the planet's habitability, and that will still be recognizably itself when our star has exhausted its hydrogen and expanded into a red giant. This is not the kind of durability that was specifically designed into the mission. It is a consequence of the properties of metal and vacuum. But it means that Voyager 1 is, in a very real sense, the most permanent thing humanity has made. And its permanence is inseparable from its distance and its silence. Because permanence in this case requires isolation from everything that would otherwise act on it. The golden record and the question of what permanent means. The golden record is the aspect of Voyager 1 that attracts the most popular interest and the most philosophical reflection, and it deserves examination not only in terms of what it contains, but in terms of what it means that it will exist, largely unchanged, for billions of years in interstellar space. The record is a physical object, a pressed and gold-plated disk, and its longevity is a physical fact, not a sentiment. Understanding what that physical fact means requires distinguishing between several different senses in which the word permanent might be applied to it. In the first and most straightforward sense, the record is permanent in the sense that it will not degrade significantly in the space environment over any timescale relevant to human concerns. Gold does not oxidize. Copper, protected by its gold plating, resists corrosion. Aluminum, the cover material, develops a thin oxide layer that then protects against further degradation. In the vacuum of interstellar space, with no oxygen, no water, no chemical agents, and no biological activity, these materials are not subject to the weathering processes that degrade all human artifacts on Earth. The primary degradation mechanism in interstellar space is micrometeorite impact, the collision of microscopic dust grains with the record's surface. At the density of particles in the interstellar medium, the cumulative effect of micrometeorite erosion over 1 billion years is estimated to remove a layer of a few micrometers from the record's surface, which is insufficient to erase the encoded information in the deeper grooves. The record will be readable by any sufficiently advanced civilization that finds it for at least 1 billion years after its departure, and possibly much longer. In the second sense, the record is permanent in the sense that the information it contains will travel with the spacecraft indefinitely. The 115 images, the greetings in 55 languages, the sounds of Earth, the 90 minutes of music, all of it encoded in the physical grooves and photographic etchings of the disk, will persist as a physical record for as long as the disk remains intact. The record carries the sound of a human heartbeat, the sound of rain, the sound of wind, the sound of a newborn crying, the sound of surf, the sound of whale calls. It carries music composed by human beings who are alive and conscious, experiencing the world with sensory and emotional richness, and who died thousands of years ago in some cases. It carries greetings from people whose names are not recorded, speaking in languages that in some cases are no longer spoken on Earth. This information will travel through the galaxy long after the human beings who recorded it and the civilization that sent them have passed through whatever transformations history has in store. In the third and most profound sense, the record's permanence raises a question that it cannot answer. Permanent for whom? Permanence implies an audience, a future reader, a civilization capable of intercepting the spacecraft and decoding what it carries. The probability of any such event occurring is, by any honest assessment, extraordinarily small. The galaxy is so large and so empty that the probability of any object crossing within detection range of any civilization over billions of years of drift through the interstellar medium is negligibly small. Voyager 1 will almost certainly never be found. The golden record will almost certainly travel undisturbed and unread through the Milky Way, until either it is destroyed by a collision, which is also a very low probability over any short timescale, but becomes significant over billions of years, or it outlasts the galaxy itself in some far future transformation of cosmic structure. Carl Sagan's answer to this apparent futility was that the record's value was not contingent on its being found. The act of choosing what to include, of deciding what sounds and images and music best represented the civilization that built Voyager 1, was itself an act of self-reflection and self-definition that had value independent of any recipient. The record exists as evidence of what humanity was at a specific moment in its history. A civilization curious enough to build something that went beyond the solar system, thoughtful enough to include a message with it, and humble enough to not assume the message would ever be received. These qualities, if they persist and develop in the civilization that Voyager 1 left behind, are what will eventually make the difference between a species that remains confined to one solar system and a species that eventually crosses the distance that Voyager 1's trajectory traces. The record is a portrait of a civilization at the beginning of its reach, sent ahead into the space it hopes one day to cross. There is also a fourth sense in which the golden record is permanent, and it is the most physically interesting of all. The record is not simply preserving information across space, it is preserving information across time. Most human records are vulnerable to the instability of the environments that surround them. Libraries burn, hard drives fail, languages evolve, civilizations collapse. Even the most durable monuments on Earth are subjected continuously to erosion, tectonic activity, biological growth, and chemical weathering. The golden record escapes almost all of these processes by leaving the environment in which they occur. In 1 billion years, the continents of Earth will have been rearranged by plate tectonics. Mountain ranges will have risen and vanished. Most species alive today, including humanity itself, may be extinct or transformed beyond recognition. The languages encoded on the record will almost certainly be unrecognizable to any descendants of the people who speak them today. Yet the physical grooves containing those languages may still exist, drifting through interstellar space largely unchanged. This creates a striking asymmetry. The record may survive far longer than the civilization that built it. It may persist longer than every nation, institution, religion, and cultural tradition that existed when it was launched. In that sense, Voyager 1 is not merely carrying a message from humanity. It is carrying a snapshot of a specific moment in human history, frozen into metal and launched into an environment where time passes differently than it does on planets. Whether anyone ever discovers it is almost beside the point. The record demonstrates that information, when embedded in sufficiently stable matter and placed in a sufficiently stable environment, can outlive the societies that created it by timescales measured not in centuries or millennia, but in geological and astronomical eras. It is a small experiment in permanence, conducted on behalf of a species whose own permanence remains uncertain. In 300,000 years, the Sun becomes a stranger. By the time 300,000 years have passed since Voyager 1's launch, the spacecraft will be approximately 161 trillion kilometers from the Sun, or roughly 17 light-years. At this distance, the Sun will still be visible from Voyager 1 as a bright star, perhaps the brightest single point of light in its sky, depending on which nearby stars happen to be closest at that moment in galactic time. But it will be recognizably a star among stars, rather than the enormous, overwhelming object it is from Earth. The 8 planets of the solar system will be entirely invisible, even in principle without technology far beyond anything currently existing. Earth, the blue dot that Carl Sagan named and celebrated, will be lost entirely in the unresolvable glow of its host star, smaller against that background than an atom is against a basketball. The entire civilizational history of humanity, every empire and invention and tragedy and triumph, will be associated with a single point of light that Voyager 1 left behind 300,000 years earlier. 300,000 years is a time frame that geology begins to take seriously. It is long enough for significant climate shifts to occur on Earth, for coastlines to change through sea level variation and tectonic movement, for river systems to alter their courses, for mountain ranges to erode measurably. In evolutionary terms, 300,000 years is sufficient time for measurable genetic divergence between isolated populations, and in the human lineage it encompasses the entire known existence of anatomically modern Homo sapiens. The oldest known fossils of Homo sapiens date to approximately 315,000 years ago, discovered at the site of Jebel Irhoud in Morocco. From the moment the first anatomically modern human drew breath somewhere in Africa to the present day, approximately 315,000 years have elapsed. In that same span of time, Voyager 1 will travel roughly 17 light-years from the Sun. What lies at 17 light-years from the Sun in the direction Voyager 1 is travelling is not precisely known, because the stellar neighbourhood at this distance is not perfectly mapped, and because stellar positions change over 300,000 years due to proper motions. Several known stars currently lie within a few light-years of this distance in various directions. Epsilon Eridani at approximately 10.5 light-years, Ross 128 at approximately 11 light-years, and several others in the 12 to 18 light-year range. Whether Voyager 1 passes within any noteworthy distance of any of these systems depends on the detailed geometry of trajectories that cannot be predicted precisely over this timescale, because the gravitational perturbations of all the stars in the solar neighbourhood accumulate uncertainty over such long periods. What is certain is that Voyager 1 will not pass within 1 light-year of any star during the next several 100,000 years based on current calculations, making its journey a true passage through the void, rather than any kind of stellar visitation. The interstellar medium that Voyager 1 crosses during this period will vary somewhat as it moves through different regions of the local interstellar environment. The local bubble of low-density interstellar material currently surrounding the solar system is roughly 300 light-years across. Voyager 1 will remain within the local bubble for its entire 300,000-year journey to 17 light-years, and will not reach the denser surrounding medium for many millions of years. Within the local bubble, the interstellar medium is relatively sparse and hot, the remnant of the supernova explosions that excavated the cavity roughly 10 million years ago. The spacecraft moves through this environment at 17 kilometers per second, encountering approximately 1 atom per cubic centimeter on average, crossing the equivalent of the Earth-Moon distance in terms of matter content roughly every few hundred years at this density. The cumulative effect on the spacecraft's surface is gradual erosion and pitting on a microscopic scale, the same process that slowly grinds down any exposed surface in space, but operating over timescales long enough to leave visible marks on unprotected materials. The golden record attached to Voyager 1's exterior will experience this erosion as a gradual loss of material from its outer surfaces, but calculations suggest that the encoded information in the disk's grooves will remain intact for at least 1 billion years under these conditions. At 300,000 years, the record is as readable as the day it was pressed. The images, sounds, and music it carries from a civilization that has not existed for hundreds of thousands of years are all still there, encoded in the physical reality of a disk that no longer has any civilization to return to or any known recipient to play it. In 1 million years, a position that redefines small, at the 1 million year mark, Voyager 1 will be approximately 537 trillion kilometers from the Sun, which translates to roughly 56.8 light-years. This is the number that most dramatically illustrates the mismatch between human timescales, human technology, and cosmic distances. 1 million years of continuous travel at 17 kilometers per second, traveling every second of every day without pause, without slowing, without any interruption, produces a distance of 56.8 light-years. The Milky Way galaxy is approximately 100,000 light-years across. The galaxy's disk is roughly 1,000 light-years thick in the region the solar system occupies. In 1 million years, Voyager 1 will have travelled approximately 0.057% of the galaxy's diameter. It will not have crossed the galaxy's thickness in the perpendicular direction. It will be sitting, in galactic terms, essentially where it started, in the same general neighbourhood of the Orion Arm, the same segment of the Milky Way's spiral structure, the same local pocket of the galaxy that the solar system has occupied for billions of years. 1 million years is the timescale at which human evolution becomes significant. In 1 million years from now, the biological descendants of Homo sapiens, if any exist, will almost certainly be different from modern humans in measurable ways, assuming no radical technological intervention in human biology. 1 million years ago, the dominant hominin on Earth was Homo erectus, a species that used fire, made stone tools, and ranged across Africa and Eurasia. But that was cognitively and anatomically distinct from modern humans in ways that would be immediately apparent to any observer. Between Homo erectus and modern Homo sapiens, approximately 1 million years of evolution and a series of speciation events intervened. Whatever human biology looks like in 1 million years, it is likely to have changed at least as much. And yet Voyager 1 will look essentially as it did when it was launched. The metal structure will bear the accumulated pitting from 1 million years of micrometeorite impacts. The paint will be deeply degraded from cosmic ray bombardment and ultraviolet exposure. Though in the interstellar medium far from any star, the ultraviolet environment is much weaker than in the solar system. The plastic components will have undergone significant radiation damage from galactic cosmic rays, becoming brittle and potentially fractured. The electronic components will be entirely non-functional, their semiconductor materials long since altered beyond use by the accumulated radiation dose. The plutonium in the RTGs will have decayed significantly, though with a half-life of 87.7 years. After 1 million years, the plutonium will have undergone roughly 11,400 half-lives, leaving an essentially negligible residue of the original material. The thermoelectric junctions will be cold, the transmitter silent, the attitude control long since failed. But the aluminum structure, the titanium fasteners, the gold-plated copper disc, these will be functionally intact, physically recognizable as artifacts of human technology to anyone capable of finding and examining them. The star patterns visible from Voyager 1's position at 56.8 light-years will be completely unrecognizable by comparison with the night sky as seen from Earth today. 1 million years of stellar proper motions will have rearranged the nearby stars so dramatically that the familiar constellations of the present sky will bear no resemblance to what surrounds Voyager 1 at this epoch. The Sun itself, at 56.8 light-years, will be a moderately bright star, perhaps similar in apparent brightness to how Vega or Capella appear from Earth today. Bright enough to be among the more prominent stars in the sky, but unremarkable, easily lost in the surrounding stellar field. It will be one point of light among thousands. Earth will be entirely invisible without a dedicated telescope of extraordinary power aimed at precisely the right coordinates. In 1 million years, the civilization that built Voyager 1 will either have been transformed beyond recognition by technological and biological evolution, collapsed and been replaced by successor civilizations, extended itself across the solar system and potentially to other star systems, or ceased to exist. The golden record it sent with Voyager 1 will still carry its encoded portrait of humanity as it was in 1977. In a sense, the record will be a more accurate representation of what humans were at the height of the civilization that sent it than any surviving artifact on Earth, because Earth's record of the late 20th century will be buried under geological processes, degraded by time, and interpreted through the lenses of cultures that may be entirely different from those of 1977. The record, in its aluminum cover in interstellar space, will still have the same grooves, the same images, the same sounds, unchanged. The stellar encounters across the deep future. The question of which stars Voyager 1 will pass closest to across the deep future, beyond the 40,000-year encounter with the star in Camelopardalis described in Part 1, can be partially answered by tracing known stellar proper motions forward in time, though the predictions become increasingly uncertain beyond a few 100,000 years as small errors in current velocity measurements accumulate. Several astronomers and research groups have calculated the future stellar encounters of Voyager 1 and the other Voyager and Pioneer spacecraft, and the results constitute a kind of itinerary for a traveller who will never know it has one. After the closest approach to AC plus 79 3888 in approximately 40,000 years at a distance of 1.6 light-years, Voyager 1's next notable stellar encounter is a pass within approximately 0.3 light-years of the star TYC 313552-1 in approximately 230,000 years. This is the closest confirmed approach Voyager 1 will make to any star system in the calculable future, based on current stellar catalogue data, and 0.3 light-years is still approximately 2.8 trillion kilometres, far closer than anything in Voyager's current neighbourhood, but still an encounter in which the spacecraft will not approach any planetary system within any realistic detection range, and will experience negligible gravitational influence from the star. At approximately 4 million years from now, calculations suggest Voyager 1 will pass within approximately 1.7 light-years of the star Ross 248, a nearby red dwarf at approximately 10.3 light-years from Earth today, but moving in a direction that will bring it significantly closer to the solar system before eventually receding. This same star, Ross 248, also appears in Voyager 2's future trajectory, with Voyager 2 passing somewhat closer to it in a slightly different time frame. The repeated appearance of Ross 248 in the future stellar encounter lists of the Voyager probes is a consequence of its high proper motion and the geometry of the Voyager trajectories, not of any special property of the star itself. Ross 248 is an M-type red dwarf with no confirmed planets, and its significance in Voyager's future is entirely a matter of being in the right part of the sky at the right time relative to the probe's trajectories. Beyond 4 million years, the predictions become increasingly uncertain as the accumulated effects of gravitational perturbations from the many stars the Voyager probes will have passed become impossible to calculate precisely. The trajectories are effectively chaotic on these timescales in the mathematical sense that small uncertainties in initial conditions, in the current velocity of Voyager 1 or in the velocities of the stars it passes, grow exponentially with time to produce large uncertainties in position. This is not a limitation of computation, but a fundamental property of dynamical systems with many interacting bodies. What can be said with confidence is that Voyager 1 will continue moving through the galaxy in the general direction of its current trajectory, gradually having its path bent by the gravitational influence of passing stars, and will eventually, over millions to tens of millions of years, be scattered into a trajectory that bears less and less resemblance to its original direction from the solar system. The closest any of the encounters listed above comes to what a person might imagine as a dramatic stellar flyby is TYC 313552-1 at 0.3 light-years, which in everyday terms is still 2.8 trillion kilometres. For comparison, the distance from the Sun to the nearest star today is 4.24 light-years, and 0.3 light-years is roughly 1/14 of that. It represents the space between a star and the inner boundary of its Oort cloud, if it has one. No planet orbits any known star at 0.3 light-years from that star. The encounter is an astronomical near-miss in the sense that no human instrument could have produced a close-up view of this encounter, even if operating. But in physical terms, it involves two objects separated by a distance light takes over 3 months to cross, with no physical interaction between them beyond the negligible gravitational deflection that this mass at this distance produces. What these encounters collectively illustrate is that the Milky Way is not a place of frequent stellar encounters. Stars are separated by distances so vast that even Voyager 1, travelling continuously for hundreds of thousands of years, makes only occasional approaches to other star systems, and those approaches are themselves measured in fractions of a light-year, not in anything resembling proximity. The galaxy is a place of profound separation, where stars drift in their orbits around the galactic centre, separated by 4 to 5 light-years on average in this part of the Milky Way, and where the chance of any random object crossing within observable range of any planet around any star is extraordinarily small, even over geological timescales. In 10 million years, drifting into a different galactic neighbourhood. 10 million years is the timescale at which the solar system's motion around the galactic centre becomes significant for Voyager 1's story. The Sun orbits the centre of the Milky Way at approximately 220 kilometres per second, completing one full orbit called a galactic year in approximately 225 to 250 million years. In 10 million years, the Sun will have moved a significant distance along its galactic orbit, roughly 4.5% of the way through a single galactic year. The stellar neighbourhood surrounding the solar system will have changed substantially as the Sun and the local stars each follow their individual orbits around the galactic centre, drifting relative to one another as their slightly different orbital velocities and inclinations accumulate into significant positional differences over millions of years. Voyager 1, by contrast, is not orbiting the galactic centre in the same sense that the Sun is. It departed the solar system with a velocity of 17 kilometres per second relative to the Sun, which adds to the Sun's galactic orbital velocity of 220 kilometres per second to give Voyager 1 a total velocity relative to the galactic centre of approximately 234 kilometres per second in the direction composed of both vectors. The probe is following a roughly galactic orbital trajectory because the dominant velocity component is inherited from the Sun. But it is not gravitationally bound to the Sun, and over millions of years it will drift along a slightly different galactic orbit than the Sun follows, gradually separating from the solar system's position in the galaxy. In 10 million years, Voyager 1 will have travelled approximately 568 light-years from its launch point. At this distance, it has moved roughly 0.57% of the galactic diameter and a measurable fraction of the galactic disk's local thickness. The solar system in 10 million years will be in a slightly different position along its galactic orbit than it is today, and Voyager 1 will be in a direction from the Sun that no longer corresponds precisely to the direction in which it was launched, because the relative drift of Voyager 1 and the Sun over millions of years will have accumulated into a significant angular separation. 10 million years is also the timescale at which significant geological change occurs on Earth. 10 million years ago, the Rocky Mountains were higher than they are today. The Himalayas were still rising at a geologically rapid rate. The Mediterranean Sea had a different shape, and the land bridge between North and South America did not yet exist. The Atlantic Ocean was narrower. Africa and Eurasia had a different relative position. In 10 million years from now, the continents will again be in different positions relative to each other. The Himalayas may have eroded significantly, and the Mediterranean may have dried and refilled again. Whatever physical traces remain of human civilization on Earth after 10 million years will be subtle. Perhaps specific isotopic signatures in rock layers marking the period of industrial civilization. Perhaps fossil evidence of the distinctive assemblage of species associated with human-altered ecosystems. The specific artifacts and monuments that seem permanent to us now will be gone entirely, dissolved by weathering, buried by sediment, or incorporated into rock formations. Against this geological time horizon, Voyager 1's 568 light-year position represents the most durable physical object humanity has produced in terms of its relationship to our current epoch. Not a mountain, not a rock formation, not a sedimentary layer, but a piece of engineered metal carrying a golden record is what survives for 10 million years, recognizably human in origin, physically intact in its basic structural form, moving through the galaxy at the same velocity it had in 1977. The irony is striking. We struggle to leave any mark on our own planet across geological time, but we have sent an object into space that will outlast the geological record of our existence here. In 100 million years, beyond the scale of life on Earth. At the 100 million year timescale, the comparison of Voyager 1's journey to anything in human experience, or even in Earth's biological history, becomes strained to the breaking point, because 100 million years is longer than most species survive before going extinct or evolving into something else, and it is the timescale over which the solar system completes a significant fraction of one full galactic orbit. In 100 million years, Voyager 1 will have travelled approximately 5,680 light-years from its launch point. This represents about 5.7% of the galactic diameter, or about 22% of the distance from the solar system to the galactic centre. Voyager 1 will have crossed from its origin point in the Orion arm of the Milky Way into a significantly different region of the galactic disk. 100 million years ago on Earth, the dinosaurs were in the middle of their Cretaceous dominance. Flowering plants had recently evolved and were beginning to diversify into the enormous variety of forms that now characterize terrestrial ecosystems. The Atlantic Ocean was narrower than it is today. The continents were arranged differently. No grass existed. The Rocky Mountains had not yet risen. No mammal was larger than a small dog. The biological world of 100 million years ago would be alien to any person dropped into it, despite being the same planet producing the same general type of complex life. In another 100 million years, the biological world of Earth, if Earth still hosts life, will be equally unrecognizable. And Voyager 1 will be at 5,680 light-years, moving through whichever region of the galactic disk it happens to be traversing. By this point, the Sun will have completed a significant fraction of a galactic orbit and will be in a different position relative to the galactic spiral arms. The stellar neighbourhood through which Voyager 1 is travelling will bear no resemblance to the local neighbourhood from which it departed. It will be moving through a statistically typical region of the Milky Way's disk, surrounded by stars at the average galactic density for that region, occasionally passing within a few light-years of a stellar system, never approaching close enough to any star to interact physically, continuing on its trajectory with the same velocity it has maintained for 100 million years. The physics of the spacecraft's survival to this point is straightforward. In the vacuum of interstellar space, no corrosion occurs. No thermal cycling degrades the structure because the temperature is constant. The only degradation mechanisms are cosmic ray bombardment, which alters the crystal structure of materials and causes embrittlement over long timescales, and micrometeorite impacts, which slowly erode exposed surfaces. Over 100 million years, the cumulative effects of these processes will have altered the spacecraft meaningfully. The outermost surfaces will have been significantly eroded. The structural materials will have become more brittle, and any polymer components will be heavily degraded. But the core metallic structure, particularly the denser and more radiation-resistant elements, will retain structural integrity. The golden record, with its gold plating protecting the information-bearing copper, will have lost some surface material to erosion, but will retain the information encoded in its deeper grooves. The total cosmic ray dose received by any location on the spacecraft over 100 million years, at the flux levels typical of the local interstellar medium, is approximately 10 to the 7th rads, or 100,000 Gray in SI units. This is a dose sufficient to cause significant physical changes in most materials, including discoloration, embrittlement, and loss of mechanical properties. Biological tissue at this dose would have been lethal billions of times over. But metals and ceramics are far more resistant, and the critical question for the record is whether the grooves retain their physical geometry rather than whether the material retains its mechanical properties. As long as the groove geometry is preserved, the information can in principle be read. In 1 billion years, the galaxy has changed around it. By the time 1 billion years have elapsed since Voyager 1's launch, the spacecraft will be approximately 56,800 light-years from the Sun, or slightly more than half the diameter of the Milky Way's disk. The Sun itself, over 1 billion years, will have completed 4 full galactic orbits and will be in approximately the same relative position in the galaxy that it occupies today, having traced a nearly closed orbit around the galactic center that returns it to a region similar to its current location. But Voyager 1, on a slightly different trajectory with a slightly different velocity, will have drifted far from the solar system's current neighborhood. 1 billion years is the timescale at which the Sun's evolution becomes significant for Earth's habitability. The Sun increases in luminosity by approximately 10% per billion years as hydrogen in its core is converted to helium, and the core contracts and heats slightly. In approximately 1 billion years, the Sun's increased luminosity will have intensified the greenhouse effect on Earth to the point where surface temperatures exceed what Earth's biosphere can tolerate, potentially triggering a runaway greenhouse effect that evaporates the oceans over a period of hundreds of millions of years. By 1 billion years from now, the Earth may be uninhabitable, its oceans gone, its surface temperature hundreds of degrees higher than today, its atmosphere stripped or dramatically altered. Voyager 1 will have been moving silently through the galaxy for the entirety of this process, indifferent to the fate of the planet that built it. The Andromeda Galaxy, currently approximately 2.537 million light-years from the Milky Way and approaching at roughly 110 kilometers per second, will have begun its merger with the Milky Way by approximately 4 to 5 billion years from now. In 1 billion years, Andromeda will be noticeably closer to the Milky Way in the night sky as seen from any surviving planet, its apparent size visibly larger than it appears today. The interaction of the two galaxies' gravitational fields will have begun to distort the outer regions of both galaxies, though the actual collision of the central regions is not expected for approximately 4 to 5 billion years. Voyager 1, at 56,800 light-years from the Sun in 1 billion years, may find itself in a region of the Milky Way's disk that begins to experience the gravitational influence of the approaching Andromeda Galaxy, adding a perturbation to its trajectory that could alter its path in ways that are entirely unpredictable from any current calculation. What is remarkable about Voyager 1 at the 1 billion year timescale is not that it will have travelled far, though 56,800 light-years is legitimately impressive by any human measure. It is that it will still be moving, still intact in its basic metallic structure, still carrying its golden record, still following a trajectory set by the thrust of a rocket engine that burned for a few minutes in 1977. No other artifact of human civilization will be as old, as distant, or as physically present in the universe. Every building humanity has built will be dust. Every book will be gone. Every digital record will be lost through the failure of the media it is stored on long before this time scale. Every organism descended from today's life will either be extinct or so different as to share nothing but a distant genetic ancestry. But Voyager 1 will still be there, moving at 17 kilometers per second through a galaxy that has changed enormously around it, carrying a disk pressed with sounds and images of a civilization that ended 1 billion years earlier. The 1 billion year mark also highlights a deeper truth about the difference between astronomical and biological timescales. Evolution on Earth transformed simple microbial life into complex multicellular organisms in less time than Voyager 1 will have spent crossing half the galaxy. Entire branches of life appeared, flourished, and vanished within intervals shorter than the spacecraft's journey. From Voyager's perspective, if such a perspective could exist, civilizations are brief flashes, species are temporary. Even planets are transient environments whose conditions change dramatically over geological time. Meanwhile, the Milky Way itself will continue its slow evolution. New stars will form from collapsing molecular clouds, while older stars exhaust their nuclear fuel and die. Some will end as white dwarfs, others as neutron stars, and the most massive as black holes. Voyager 1 will pass through a galaxy whose stellar population is gradually changing around it, yet the spacecraft will remain an artifact of a much earlier era. Its materials will bear the scars of 1 billion years of radiation damage and micrometeorite erosion, but its overall form may still be recognizable to a sufficiently advanced observer. In this sense, Voyager 1 becomes something more than a spacecraft. It becomes a time capsule moving through cosmic history, carrying physical evidence that intelligent life once emerged around an ordinary yellow star and briefly learned how to send objects beyond its home world. Long after the circumstances of its creation have vanished, the artifact itself will continue the journey, preserving a small fragment of that story in metal, gold, and motion. The physics of why it never stops. The fact that Voyager 1 will continue moving indefinitely, without any engine, without any active maintenance, without any continued energy input, requires a physical explanation that is both simple and counterintuitive for anyone whose experience of the world is shaped by objects that slow down when not propelled. On Earth, everything that moves eventually stops. A rolling ball slows because friction from the ground and air resistance remove kinetic energy. A car coasts to a halt when the engine stops because air resistance and tire friction continuously drain energy from its motion. A satellite in low Earth orbit gradually loses altitude because even the uppermost atmosphere exerts enough drag to slowly reduce the orbital energy. The assumption that moving things slow down and stop is so deeply embedded in everyday experience that the assertion that Voyager 1 will never stop seems counterintuitive, as if something must be wrong. What is wrong is the generalization. Moving things slow down when forces act on them to remove kinetic energy. In the absence of such forces, Newton's first law of motion, first stated formally in 1687, but representing a principle of mechanics that is as fundamental as any in physics, states that an object in motion continues in motion at constant velocity. On Earth, such forces are always present: friction, air resistance, gravity, pulling objects toward the surface. In interstellar space, these forces are absent or negligibly small. There is no air, so there is no air resistance. There is no surface, so there is no friction. The gravitational influence of any individual star at distances of light years is so small, approximately 10 to the negative 14 g for a solar mass star at 1 light-year distance, that it produces an acceleration of roughly 3 centimeters per second over 1,000 years. Orders of magnitude too small to matter in any practical sense over the timescales of Voyager 1's journey. The spacecraft is effectively in free space, subject to no meaningful force. The interstellar medium itself, while not perfectly empty, is so sparse that its drag on a spacecraft moving at 17 kilometers per second is completely negligible. The total momentum transferred from interstellar medium particles to the spacecraft over 1 million years of travel, at the local interstellar medium density of approximately 1 atom per cubic centimeter, is a tiny fraction of the spacecraft's own momentum. The spacecraft is enormously more massive than all the interstellar medium particles it encounters in any reasonable time period. The interaction is like a bus hitting individual raindrops. Each individual impact is negligible, and even the cumulative effect over extremely long periods produces no measurable change in the spacecraft's velocity. The deeper physical principle underlying this behavior is conservation of momentum. In the absence of external forces, the total momentum of an isolated system is constant. Voyager 1, after its last thruster firing, became essentially an isolated object in space. Its momentum, the product of its mass and velocity, was fixed at that moment and has remained fixed since. No process in interstellar space is capable of removing that momentum on any timescale relevant to the universe's current age. The spacecraft will carry its momentum indefinitely, moving at 17 kilometers per second until something physically significant happens to it, which on the timescale of the next billion years is essentially nothing. Even the eventual death of the Sun and the transformation of the solar system will not affect Voyager 1, which by that point will be far beyond any influence that the Sun's evolution exerts on interstellar space. This permanence of motion is one of the most alien aspects of the spacecraft's future to human intuition, and it is also one of the most profound implications of the physical laws that govern the universe. The universe is not designed to stop things. Rest is not a preferred state. Motion, once established, continues. The rocks tumbling across a hillside on Earth stop because Earth is in the way. Remove the Earth, and they would travel forever. Voyager 1 has the benefit of no Earth in the way, nothing in the way, a clear path through interstellar space that will not be obstructed by anything significant for longer than the universe has existed so far. What the universe will do to Voyager 1 over billions of years. While Voyager 1's trajectory will continue without meaningful interruption for billions of years. The spacecraft itself is not entirely passive in its relationship to the universe through which it moves. Several physical processes act on it continuously, and over sufficiently long timescales, their cumulative effects become significant in ways that alter the spacecraft's structure, though not its motion. Understanding these processes is understanding what it means for a human artifact to persist in the universe over geological and astronomical time, and what eventually becomes of even the most durable things we can create. Cosmic ray bombardment is the most continuously destructive process acting on Voyager 1 in interstellar space. Galactic cosmic rays are highly energetic charged particles, primarily protons, and heavier nuclei accelerated to relativistic speeds by astrophysical processes, including supernova shock waves and the jets of active galaxies. They permeate the galaxy at a roughly uniform flux and penetrate through any thickness of material that a spacecraft might carry. Each cosmic ray particle that passes through the spacecraft deposits ionizing energy along its track, displacing atoms from their lattice positions in crystalline materials and creating chemical reactions in organic materials. Over millions of years, the cumulative displacement damage in the spacecraft's metallic components will alter their mechanical properties, making them more brittle and reducing their tensile strength. The electronic components, already non-functional long before this, will have their semiconductor crystal structures progressively destroyed. The golden record will experience some degree of surface darkening from radiation-induced chemical changes in any residual contaminants on its surface, though the gold plating itself is highly resistant to radiation damage. Micrometeorite impacts, while individually tiny, accumulate over vast timescales into a measurable surface erosion. The interstellar medium contains microscopic solid particles, primarily silicate and carbon grains, at low but non-zero density. These particles, travelling at typical interstellar velocities relative to Voyager 1, impact the spacecraft's forward-facing surfaces and deposit energy that ejects small amounts of material. The rate of this erosion depends on the particle flux and the impact velocities, which are estimated to remove a few micrometers of surface material per million years in the local interstellar medium. Over 1 billion years, this represents several millimeters of erosion from the most exposed surfaces, which is significant for thin components, but not for the bulk structure of the spacecraft. The golden record, with its recessed grooves protected within the enclosed aluminum cover, is largely shielded from direct micrometeorite impact on the information-bearing surface. The aluminum cover of the golden record is itself an interesting case study in material survival. Aluminum in vacuum is highly resistant to corrosion because it immediately forms a thin, stable oxide layer that prevents further oxidation. This oxide layer, typically a few nanometers thick, is impenetrable to oxygen in the absence of an oxidizing atmosphere. But in interstellar space, there is no oxygen atmosphere to require it. The aluminum surface is thus stable in a different sense. It does not corrode because there is no corrosive agent to react with it. The primary interaction of the aluminum with its environment is cosmic ray bombardment, which causes atomic displacement damage and micrometeorite impact, which slowly erodes the outermost surface. Over billions of years, the aluminum cover will be pitted and somewhat eroded on its outer face, but its structural integrity and its ability to protect the record inside will be maintained for at least 1 to several billion years. The plutonium in the RTGs, which provided power for the first few decades of the mission, will have decayed almost entirely to lead-206 over billions of years. The half-life of plutonium-238 is 87.7 years. So in 1 billion years, the plutonium will have undergone approximately 11.4 million half-lives, reducing the original quantity to an effectively zero fraction. The RTG housings will contain lead-206 instead of plutonium occupying the same volume, with the same mass approximately, but chemically and physically different from what was launched. The heat that the RTGs produced for nearly 5 decades will have ended long before this point, and the housings will be cold, their thermal gradient eliminated, their thermoelectric function ceased for billions of years. The spacecraft's polymers and composite materials will experience a different form of aging. Many of Voyager 1's cables, insulation layers, adhesives, and protective coatings contain long-chain molecular structures that were never designed for million-year survival. In the vacuum of space, there is no moisture or oxygen to drive conventional chemical degradation, but cosmic radiation continuously breaks molecular bonds. Over millions of years, these materials will gradually become brittle, crack, and fragment. Wire insulation will lose flexibility. Adhesive bonds that once secured components together will fail. Thermal blankets that helped retain heat during the mission's operational life will slowly deteriorate into fragile, radiation-damaged sheets. None of this will affect the spacecraft's trajectory, but it will alter its physical appearance, transforming it from a functioning machine into a collection of connected but increasingly weathered components. Gravitational encounters also leave subtle marks on the spacecraft's history. Although passing stars will not physically damage Voyager, each encounter slightly changes its path through space. Over hundreds of millions of years, these cumulative perturbations will randomize the spacecraft's orientation and trajectory relative to its original course. The antenna that once pointed toward Earth with extraordinary precision will eventually face arbitrary directions as the spacecraft tumbles slowly through the galaxy. The concept of forward and backward will lose meaning. Voyager will no longer resemble a spacecraft on a mission, but an artifact carried passively by the larger gravitational currents of the Milky Way. Yet the remarkable conclusion is that none of these processes are fast. Even after hundreds of millions of years, Voyager 1 will remain recognizable as an artificial object. Long after mountains on Earth have risen and eroded away, long after continents have rearranged themselves, and long after every human-built structure on Earth's surface has disappeared, this small machine launched in 1977 will still exist in some form. Damaged, irradiated, eroded and silent, but unmistakably manufactured. The universe is not a place that rapidly destroys objects. More often, it preserves them with extraordinary patience, allowing the traces of vanished civilizations to persist for timescales far beyond the lifetimes of the civilizations that created them. Voyager may ultimately become the longest-lasting physical artifact humanity has ever produced, not because it was designed to be immortal, but because it was launched into an environment where destruction proceeds almost unimaginably slowly. The question of whether it will ever be found. The Golden Record was designed with the explicit assumption that it might someday be found by an extraterrestrial civilization capable of decoding its contents and learning from it something about humanity. The probability of this occurring has been discussed in various contexts since the record was conceived, and the conclusions are consistently sobering. The probability that any civilization, human or otherwise, will ever intercept Voyager 1 is extraordinarily small by any honest estimate. But the question deserves careful examination because it touches on both the physics of interstellar space and the deeper philosophical question of what it means to send a message that almost certainly will never arrive. The physical basis for the low probability is straightforward. Interstellar space is so vast and so empty that the chance of any specific object crossing within detection range of any civilization over any finite time period is negligibly small. Voyager 1 has a cross-section of roughly 10 square meters. The volume of space through which it will travel in 1 million years is a cylinder of radius 1 light-year and length 56.8 light-years, approximately 10 cubic light-years. The fraction of this volume that is within 1 astronomical unit, the Earth-Sun distance, of any point that Voyager 1 actually occupies at any given time, is roughly 10 square meters times 56.8 light-years divided by the cylindrical volume. This is an incredibly small fraction, and the number of civilizations per cubic light-year that might be in a position to detect and retrieve Voyager 1 is itself an extremely uncertain but presumably small number. The product of these two small numbers produces a probability per million years that is very small. Over billions of years, the cumulative probability increases, but remains small. The trajectory of Voyager 1 across the galaxy over billions of years is not predictable precisely enough to determine exactly which stellar systems it will pass near, and the probability of passing within any star's planetary system at close enough range to be detected by any civilization using technology comparable to or exceeding current human capabilities is an extremely small number per stellar encounter. Even if Voyager 1 passes within a few light-years of 1,000 stellar systems over 1 billion years of travel, the probability that any of those systems has a civilization that detects a spacecraft of Voyager's size and characteristics is vanishingly small. What this means in practical terms is that the Golden Record is almost certainly permanent in the sense of being permanently unread. It will carry its encoded portrait of humanity through the galaxy for billions of years, without delivering that portrait to any recipient. This was understood and accepted by the people who designed it. Carl Sagan wrote that the chances of Voyager being intercepted by an extraterrestrial civilization were extraordinarily small, and that this did not make the effort worthless. The value of the Golden Record was not primarily in its potential for reception. It was in its existence as an act of reaching out, a decision by a young spacefaring civilization to include something human in the first object it sent beyond the solar system, as a statement of what that civilization was and what it valued. The impossibility of reception does not negate the meaning of the gesture any more than the impossibility of knowing the outcome negates the meaning of any human hope directed toward an uncertain future. The improbability of interception becomes even clearer when the geometry of the Milky Way is examined quantitatively. The galaxy contains on the order of 100 billion stars distributed across a disk approximately 100,000 light-years in diameter and about 1,000 light-years thick in its stellar component. Although these numbers sound immense, the average separation between neighbouring stars in the Sun's local region is still several light years. Space is not crowded. It is overwhelmingly empty. Even in the relatively dense stellar neighbourhoods of the galactic disk, a spacecraft travelling without active guidance is far more likely to spend millions of years crossing empty volumes than approaching any star closely. Voyager 1 is not navigating toward destinations. It is simply following a trajectory determined by its present velocity and the cumulative gravitational influences it experiences. Over time, nearby stellar encounters will slowly alter that trajectory. Every passing star exerts a gravitational pull. Most encounters are distant and weak, producing only tiny changes in velocity and direction. Yet over tens or hundreds of millions of years, these small perturbations accumulate. The result is that Voyager's path eventually becomes impossible to predict with precision. Not because the laws of physics fail, but because the system becomes increasingly sensitive to small uncertainties in future stellar encounters. This uncertainty has an interesting consequence for the Golden Record. There is no single future destination. There is no star system that can be identified as the record's eventual home. Instead, the record enters a statistical future in which it wanders through changing regions of the galaxy, occasionally passing near stars, more often traversing empty interstellar space. The overwhelming majority of its existence will be spent far from any planetary system. Even a close stellar passage does not significantly improve the odds of discovery. Suppose Voyager were to pass within 1 light-year of a star hosting an advanced civilization. 1 light-year is an extraordinarily small distance by galactic standards, but it remains vast in practical terms. From that distance, Voyager would be a dark object only a few meters across, reflecting almost no light and emitting no detectable signal. Finding it would require either deliberate searches for artificial objects in interstellar space or observational capabilities far beyond anything humanity currently possesses. This introduces a second layer of improbability. Not only must a civilization exist near Voyager's path, but that civilization must also possess the technology, motivation, and observational infrastructure necessary to detect an object of Voyager's size. The presence of intelligence alone is insufficient. Detection requires attention. Attention requires resources. Resources require priorities. There is no guarantee that even a highly advanced civilization would devote effort to searching for small, inactive artifacts drifting between the stars. The challenge is analogous to detecting a single grain of sand moving somewhere within an entire continent. The grain exists. Its trajectory is real. But existence alone does not imply discoverability. Most objects in the universe remain unseen, not because they are hidden, but because the universe contains too many places to look. This realization connects Voyager to one of the central questions of modern astronomy: the apparent absence of evidence for extraterrestrial technological civilizations. The Milky Way is billions of years old. Many stars are older than the Sun. If technological civilizations arise frequently and survive for long periods, one might expect the galaxy to contain numerous detectable artifacts, probes, beacons, or engineering projects. Yet despite decades of increasingly sensitive searches, no unambiguous evidence has been found. This observation is often discussed in connection with the Fermi paradox, the apparent contradiction between the vast number of potentially habitable worlds and the lack of confirmed extraterrestrial civilizations. Voyager's Golden Record provides an unusually concrete perspective on the problem. If humanity's first interstellar artifact is already almost impossible to find, then perhaps the galaxy could contain many similar artifacts from many civilizations, without any of them ever encountering one another. The difficulty may not be that civilizations are rare. It may be that distances are large. A technological species could build probes, launch messages, and leave artifacts that survive for millions or billions of years, while still remaining effectively invisible to everyone else. The silence of the galaxy may reflect geometry rather than absence. There is also the question of civilization longevity. The golden record may survive for billions of years, but its creators almost certainly will not. Human civilization has existed in anything resembling its modern form for only a tiny fraction of recorded history. Industrial civilization is only a few centuries old. Spaceflight is less than a century old. The timescales relevant to Voyager's journey are thousands or millions of times longer than the timescales over which human institutions have demonstrated stability. As a result, the golden record may ultimately outlive not only every person who helped create it, but every nation, language, culture, and social system that existed when it was launched. Future civilizations on Earth, if they exist, may be as different from present humanity as modern humans are from the first agricultural societies. Voyager therefore functions not merely as a message to extraterrestrials, but as a message to the future itself. This possibility creates an unexpected inversion. The most likely civilization to ever understand the golden record may not be an alien civilization at all. It may be a distant descendant of humanity. A future human society possessing advanced interstellar capabilities could conceivably recover Voyager long after its launch, treating it as both an archaeological artifact and a historical document from the earliest era of space exploration. In that sense, the golden record occupies a unique category among human creations. Most records of civilization remain on Earth, vulnerable to geological processes, climate change, war, neglect, and time itself. Voyager carries its record beyond those vulnerabilities. It is not immortal, but it is unusually insulated from the forces that erase history. The information encoded on the disk may survive longer than any library, monument, archive, or digital database humanity has ever constructed. Whether anyone ever reads it remains unknown. Physics provides no answer to that question. The laws of motion can predict where Voyager will travel. Materials science can estimate how long the record will endure. Probability theory can estimate the likelihood of interception, but meaning lies outside those calculations. The golden record exists at the intersection of science and aspiration, a durable object carrying fragile information, launched into an environment so vast that discovery is unlikely, yet preserved long enough that the possibility never entirely disappears. For billions of years, as stars orbit the center of the galaxy and civilizations rise and fall on worlds that Voyager will never see, the record will continue its journey. Silent, unread, unchanged. Not because it was expected to succeed, but because some messages are worth sending even when the universe offers no guarantee that anyone will ever hear them, what Voyager 1's journey finally means. The trajectory of Voyager 1 through time followed carefully from the present to 1,000 years, 10,000 years, 100,000 years, 1,000,000 years, 10 million years, 1,000,000,000 years, and beyond, is a lesson in what the universe actually is, in contrast to what human intuition suggests it to be. Every number in this trajectory is an education in the specific ways that cosmic scale differs from human scale, and in the specific ways that the universe does not care about human categories of distance, time, or significance. Following Voyager 1 into the future is a way of taking those abstract lessons and making them concrete, attached to a real object that real people built and launched, so that the education comes with a handle that the mind can grip. One of the things that Voyager 1's trajectory teaches is about distance. The solar system is very large by human standards and completely negligible by interstellar standards. The nearest star is 4 light-years away, and in 1,000 years of travel at the fastest sustained velocity humanity has ever achieved, Voyager 1 covers slightly more than 1% of that distance. In 1,000,000 years, it covers the distance to the nearest star and finds itself still essentially in the same galactic neighborhood it departed from. The galaxy is so large that 1,000,000 years of travel does not produce a crossing of even 1% of it. The universe is so large that 1 billion years of travel during which the spacecraft crosses roughly half the galaxy's diameter, does not produce a departure from the galaxy into the intergalactic void. These are not metaphors for largeness. They are precise physical facts about the object built by the civilization that is currently the only one known to exist in the observable universe. Another factor Voyager 1's trajectory teaches is about time. The timescales on which its journey becomes interesting are timescales that exceed all of human history by orders of magnitude. Timescales on which human biology changes, on which geological landscapes transform entirely, on which the sun's evolution begins to threaten Earth's habitability. These timescales are not merely long. They are long in a specific way that redefines what we mean by civilization, by permanence, and by legacy. Voyager 1 will be more durably present in the universe than any other artifact of human civilization. And it will be so because it escaped the processes of erosion, weathering, and biological interaction that destroy everything on Earth. Its permanence is the permanence of something that left the conditions that make permanence impossible on Earth and entered the conditions where the physics of vacuum makes it nearly inevitable. The third thing Voyager 1's trajectory teaches is about smallness and about what smallness means in a universe this large. Voyager 1 is a small machine built by small organisms on a small planet orbiting an ordinary star in an ordinary part of an ordinary galaxy. It is among the most distant objects from Earth that have ever existed, and it has been travelling for nearly 50 years, and in 1,000,000 years it will have barely scratched the surface of the galaxy around it. This smallness is not depressing if it is understood correctly. It is clarifying. It specifies precisely where humanity is in the development of its relationship to the cosmos. At the very beginning, taking the very first steps, having just barely, as a species, learned to leave the planet it formed on. The distance to the nearest star is not a measure of how far we have come. It is a measure of how far there is to go. And Voyager 1, the farthest thing humanity has ever sent, is the clearest possible statement of exactly where the starting line is. And perhaps the most important thing Voyager 1's trajectory teaches is about probability. Human intuition evolved in environments where encounters are common. On Earth, objects moving through space eventually hit something. A stone thrown through the air lands. A ship crossing an ocean reaches another shore. A traveller moving across a landscape eventually meets other travellers. The galaxy does not work that way. The distances are so large relative to the sizes of stars, planets, and spacecraft that most motion through the galaxy occurs in complete isolation. Voyager 1 will pass through regions containing billions of cubic kilometres without encountering anything larger than microscopic dust grains. Even over millions of years, the probability of a collision with a star, planet, or other macroscopic object remains extraordinarily small. The spacecraft's future is not one of destinations, but of continued transit. This distinction matters because it reveals something fundamental about the architecture of the universe. Space is not primarily a collection of objects, it is primarily emptiness. Stars appear numerous when viewed from Earth because they are bright, but brightness disguises rarity. The average distance between neighbouring stars in the Sun's region of the galaxy is measured in light years. If the Sun were reduced to the size of a marble, the nearest star would still be hundreds of kilometres away. Voyager 1's journey is therefore not primarily a journey through places. It is a journey through the vast emptiness that separates places. The fifth thing Voyager 1's trajectory teaches is about history. Human history feels ancient because it encompasses all recorded civilization. The pyramids are approximately 4,500 years old. Agriculture emerged roughly 12,000 years ago. Written language appeared about 5,000 years ago. These numbers dominate our sense of the past because they contain everything we normally think of as human achievement. Yet on the timeline of Voyager's future, all of recorded history is a brief moment. In the time it takes Voyager 1 to travel a single light year, entire civilizations could rise and disappear many times over. Languages could emerge, evolve, fragment, and vanish. Technologies that seem revolutionary today could become as obscure as Bronze Age metallurgy appears to modern engineers. In 74,000 years, roughly the time Voyager would need to reach the distance of Proxima Centauri if it were travelling in that direction, humanity's future is essentially impossible to predict. 74,000 years ago, modern humans were living alongside other human species, including Neanderthals. Agriculture did not exist. Cities did not exist. Writing did not exist. Asking what human civilization will look like 74,000 years from now is therefore equivalent to asking a hunter-gatherer living during the last ice age to predict the modern world. The scale of time defeats prediction. The sixth thing Voyager 1's trajectory teaches is about the relationship between technology and nature. The spacecraft is an extraordinary technological achievement. It crossed the outer planets, left the heliosphere, entered interstellar space, and continues operating nearly half a century after launch. Yet when viewed against astronomical scales, even this achievement appears modest. Voyager's velocity, extraordinary by human standards, is only about 0.006% of the speed of light. The galaxy contains stars moving faster. It contains pulsars moving hundreds of kilometers per second. It contains matter accelerated by black holes to velocities approaching light speed itself. The universe routinely performs feats of energy and motion that exceed the greatest accomplishments of human engineering. This perspective does not diminish the achievement, it contextualizes it. Voyager 1 is remarkable not because it rivals the scale of the cosmos, but because it represents the first successful attempt by a young technological species to engage with that scale at all. The spacecraft is important for the same reason the first ocean-going vessels were important. They were not impressive compared to the size of the oceans they crossed. They were impressive because they marked the beginning of a relationship with those oceans. The final lesson of Voyager 1's trajectory concerns perspective. The spacecraft's future path extends far beyond any institution that currently exists. Governments will change, nations will disappear, scientific theories will be revised. Entire cultural frameworks that seem permanent today may eventually be forgotten. Through all of this, Voyager 1 will continue moving. It will cross distances measured in light years while generations succeed one another on Earth. It will remain a physical connection between a specific moment in history and a future that no living person will ever witness. And that may be the most important thing its trajectory reveals. The universe is not scaled to human lifetimes, human ambitions, or human expectations. It operates on distances measured in trillions of kilometers and timescales measured in millions and billions of years. Voyager 1 is valuable because it allows us to see those scales through something familiar, a machine built by human hands. By following its future into the deep time of the galaxy, we gain a clearer understanding not only of where the spacecraft is going, but of where humanity stands in the larger story of the cosmos. The journey of Voyager 1 is ultimately a lesson in scale, and scale is one of the most important scientific facts the universe has to teach. A trajectory beyond civilization. In some number of years between now and the mid-2030s, the last signal from Voyager 1 will fade below the ability of the Deep Space Network to detect it. On some specific day that no one yet knows, a tracking session will end with no confirmed signal, and after enough subsequent sessions confirm the same result, the mission will be formally concluded. The engineers who have maintained contact with the spacecraft will have done something that no group of humans has ever done before and may never do again. Maintained a conversation across interstellar space with a machine they launched nearly 60 years earlier, receiving data from a place no instrument had ever been, and managing the graceful decline of the most distant operational scientific station humanity has ever constructed. After that silence, Voyager 1 will continue doing the only thing that physics requires of it, moving. At 17 kilometers per second, through the interstellar medium, through the Oort cloud, through the space between stars, toward no particular destination, guided by no intelligence, powered by nothing but the momentum imparted to it by a rocket that burned for a few minutes in the summer of 1977. It will pass close to no star for 40,000 years. It will take 1 million years to cover the distance to the nearest star. It will take 1 billion years to cross half the galaxy. It will carry its golden record intact and unread through all of it. The civilization that built Voyager 1 is the same civilization that is currently asking where it will be in 1,000 years, 10,000 years, 100,000 years. That question is not primarily about Voyager 1. It is about the people asking it, and what it means for a species to have built something that will outlast everything they know, to have thrown something into the universe that is more permanent than the civilization that threw it. The answer to where Voyager 1 will be in 1 million years is moving through the galaxy at the same speed it has always moved, carrying what we sent with it. The more important answer, the one that matters for the civilization still here and still asking questions, is the one embedded in the distance it will have covered and the time it will have taken. We have barely begun, and the universe is very large, and there is everything still to do.